Good evening, everybody. Good to have you here. My name is Ashish. I'm the head of products at MapD. With me is Matthias Dubinsky, who's a Tokyo-based machine learning researcher from H2O AI. He's also working on the core H2O and sparkling water platform. He loves machine learning and hates buzzwords. Neither. Yeah. So today's session is about GPU. Today's session is about GPU-powered visualization and machine learning. Before I start the session, I'd love to get a bit of hand raise on how many people have heard of GPUs. Are you familiar with GPUs? Okay. I guess that everyone knows that. How many are you familiar with GPUs, general purpose GPUs for machine learning and data analytics? Okay. So I would say it's a good place to start to talk about what GPUs are. And I guess all of you have heard of GPUs because it's not a new concept. It's been around with, from the days of video games. That's why the GPU really came into force. And over the last few years, again, GPUs, which are general purpose GPUs, are being used extensively for machine learning, deep learning. And with MapD, we've actually used GPUs for data and analytics processing. So the big question is, we had CPUs. You know, everyone promised us the in-memory data revolution. So what's the big deal about GPUs? What's the difference? And the first thing when it comes to CPUs it's a very general purpose processing core. A typical CPU has 20 cores, and a typical GPU has almost 4,000 cores. So the number of cores is one metric to decide how much of the processing workload it can take. While the cores in a CPU are much powerful than a GPU cores, GPUs are very good for parallel processing, what they call SIMD, single instruction, multiple data. The second thing about GPUs or GPUs are they have 20 to 30x times more memory bandwidth. So they can move a large amount of data back and forth. So with that, I'm going to start talking a little bit about MapD and how we've used MapD for data and analytics. Are you familiar with MapD as the company or the products? Have you heard? Okay, tier one. So I'll spend a little bit more time on just talking about the company itself. First thing you have to understand about MapD is that MapD was coined to stand for Massive Parallel Database. So at the heart of MapD is the MapD SQL engine. It runs on GPUs. It's able to take a large amount of analytical processing on the GPU. In addition to that, we do a lot of optimizations to make it run faster, like LLVM. I'll talk a little bit about it. But in essence, you can really get a large amount of data on the GPU MapD core, which is a database engine, and process it at high speeds. Analytical processing, table scans, aggregation, filters are much faster because we take advantage of GPU parallel processing. MapD Immerse is our interactive visual analytics client. So it's a self-service platform. It sits on top of MapD. It's able to show visualizations. You interact with large amount of data at the speed of thought. Again, Matthias doesn't like buzzwords, so I will show it before so you can experience it. Before I jump onto that, let me tell a little bit about not just that MapD was built ground up to take advantage of GPUs. It's also using some smart tricks to ensure high speeds. One of it is what's called LLVM. A typical SQL function is declarative language. It goes to a query optimizer, and it carries a lot of overhead. It doesn't support vectorization. Things which are faster if you do a dynamic compilation, just-in-time compilation called LLVM, which you can target some architectures like ARM, CPU, GPUs. It inline functions, it supports vectorization. So in a sense, in addition to GPU acceleration, you're also getting a large amount of optimization because you're using LLVM as a means of query compilation. As you can see, SQL is transferred into the LLVM, and then it can run against different target architectures as well. I'll talk a little bit about MapD Immerse. As I said, it's a front-end interactive visual analytics platform. The first thing about it, it's very standards-based. We use D3 and other JavaScript toolkits for visualizing pie charts, scatter plots, a bunch of other visualizations. What is really interesting about, and mapping as well, is the fact that we use server-side GPUs. Like you said, GPUs are great in games, right? They do a lot of graphic processing. So we use OpenCL to be able to render some things which have a high density of points, like scatter plots, point maps, heat maps, on the server side, and just send back a PNG, which is composited on a base layer map. So in that sense, the two big things happen. First, it's really fast. Secondly, certain things which, when you exceed 100,000 points, you send to a browser or your client, your browser can't even handle it. It's not able to handle more than 100,000 points, for instance. This dual mechanism makes it faster and interactive, and also more secure. So you don't send data points back, so you're able to just see the visualizations. Some of the, if you're sensitive about data, that's actually very useful as well. In fact, the speed of MapD queries are orders of magnitude faster. In fact, blogger Mark, and forgive my pronunciation, Litvinenko, benchmark MapD on the billion. You have a question?
I was going to ask you, can you actually dump a bunch of LiDAR point cloud data as well?
Yeah, so the longer answer to that question is yes. I mean, one of the things which MapD, I'm talking to this just for the sake. So one of the things MapD, think of as analytical processing, think of the traditional analytical processing engines out there. You need the data to be denormalized in a star schema and mostly focus on structured data, because GPUs are great for structured data processing, not very good with variable length processing, which typically strings are not very well supported in a GPU. But from that perspective, if you're able to get it in a denormalized format, and if you're able to get it in a way you want it to be analyzed with, you can definitely do it. In fact, we have some companies looking at us with exactly that kind of use case. So there is this popular New York City taxi ride data. Have you heard of these? Maybe you haven't. It's so 1.2 billion records of taxi, Uber, Lyft ride over a 7-year period in New York City. That's the data set. It's a very popular data set used for numerous reasons. And he basically looked at the query times of running on GPUs and CPUs. So that was the basic thing. And then different software or databases run in GPU and CPU. And if you actually see, the GPUs are of magnitudes much faster than CPUs. But the first top 5 query times are MapD on NVIDIA, Pascal, Teslas, etc. So we basically not only are the king of the hill in that sense, but we are also much far ahead. If you look at the bottom pile, Spark on the cluster, and a lot of people ask, Spark is in memory, it's fast, it's having a high throughput, but has a high latency as well, right? So you can really scan the table, and you'll see that GPU database for this exact use case, which is structured data, large amount of table scans, aggregations. We are getting a response time of 21 milliseconds, 27 milliseconds. The top 5 of them are MapD. Like I said, it's easier to see it than believe it. So believe me. So let's actually jump forward. In fact, all of you can go under the demos, and we will have a bunch of demos, which includes the tweet map, ship movements, the taxi rides, and play with it yourself, and you'll be able to check, find out. So here is, hopefully you can see this, 1.2 billion rows of data right here. And as you can see, you have different ways of visualization. You have it on a geomap. with or a scatter plot out here. You have a bar chart, a heat map on the right hand side, and a time series chart here. And this is what you can think, get into the eyes or the shoes of business analysts, and they're looking at a large amount of data, and they're trying to ask questions about known unknowns, right? You're looking at things like, oh, I know, I can guess that here's like, let's actually go through it, right? Let's go to East Village. And you can see just I typed it down and it interactively in real time, in milliseconds, zoomed in and applied the cross filter across all the charts. 66, I believe, million data points. And here's a question which I have to you have to see is look at the right-hand chart, and you'll see that the heat map shows more hotter color at 2 a.m. on Saturday and Sundays. This is where the pickups are happening at. So it's very much a party neighborhood. People come here to party, right? There's more likely to come here to party during this time. You'll also see the breakdown of cash and credit. You like equal amounts of cash and credit. Let's go back in time and see, has it changed over time? So now you see I've just brushed across the time series chart down here, and for the period 2010 to 2011, and you'll see, most of the payments were done in cash rather than credit, right? And then I can quickly look at 2014 to 15, and you see credit is exceeding cash. So obviously the hypothesis that the Ubers and the Lyfts have actually taken over the market, because taxi ride you probably pay cash. Again, these are the hypothesis, speed of thought analysis you can come down to. You have a question?
I do. When you first did this filter, or when you actually painted across this part of the timeline,
I brushed across.
Yeah. Did you actually send a series of PNGs from the server, or was this sending all the points to the browser?
Right. So like I said, some of it is browser side and some of it is server side. Okay. What we call in situ rendering. Sure. These number of points, 66 million or 9 million, is all server side. It's a PNG composited on the Mapbox.
So you're actually doing a transition animation as a series of PNGs that come in the browser?
Yes, it's just a low fidelity PNG. It's just coming to the browser. So,
okay.
And then once you get it, you'll see the full resolution PNG. So that's an important question, because if you try to do this by sending 6 million points back to the browser will crash. I mean, a typical screen supports only so many raster data points. So you need to composite, or you want to render it on the server side. There's other interesting things you can come down, but you can verify that. Let's see, Times Square.
Using jitter or alpha?
Sorry?
Is it using jitter or is it using alpha?
I'm not quite sure. Maybe someone on my MapD team can answer that question. Jitter or alpha? Probably. Maybe you'll get back to you. No jitter right now. I mean, just simple hypothesis. Like I said, all the cross filters are applied across the board, so it's across all the charts. But here I just looked at Times Square, and you'll see cash is king, probably more tourists using taxi rides. So interesting things. You can explore known unknowns, unknown unknowns, really reveal the data, test a hypothesis without waiting to drink a coffee and come back. But that's what I wanted to show you. So it's easier for you to understand. Now the whole meetup is about machine learning, and let's try to define machine learning. But before that, I have to define what Go AI is, because Go AI is it's a GPU open analytics initiative, and it helped to unlock and break down the silos between different software and platforms running on GPUs. So to explain that, let's talk about what happened before Go AI, right? So before Go AI, while GPUs have 20x more memory bandwidth and 100x more processing cores than CPUs, even though a MapD or Python or H2O AI run on GPUs, if you need to share data across these two systems, you had to go through the CPU and back to the GPU. And really the limiting factor is the speed of the PCIe bus, which runs to 4 to 16 gigabytes per second. So from that perspective, your speed of your interaction actually is the speed of your slowest soldier, which was your PCIe bus. So while the GPUs are fast, you're serializing, deserializing data, and you're copying back and forth. So this is before Go AI, and as you can understand, it's memory hierarchy bottleneck out here. So the GPU Open Analytics Initiative was launched in May of this year with H2O.ai and Continuum Analytics, who have obviously renamed themselves as Anaconda. And the real goal was that how do you allow for zero copy data interchange? And that we use something called a GPU data frame, which is a container where you can share between two different software platforms running on GPUs without copying back and forth through the CPU, number one. You don't even copy at all because you just share a virtual pointer to the GDF. This is a consortium. It's an open ecosystem based on open source technologies. The GPU data frame is actually heavily based on Apache Arrow. It's an ASF project by Wes McKinley. Maybe pronounced his name wrong. And the reason he created the project was because for any step in a data value chain, from data processing to analytics processing to advanced analytics processing, there's a lot of runtime data frame being exchanged. JVM doesn't understand, Julia doesn't understand an R data frame, so you have to do copy back and forth, serialize, deserialize information, and you lose a lot of speed because of that. The GPU data frame then allows you to do this with zero copy. The consortium has grown extensively. We have Anaconda, like we said, we started with them, Graphistry, Gunrock, PyTorch, TensorFlow, and BlazingDB. So it's a growing list of players who are taking advantage of GPUs and breaking down the silos between GPUs as well. So this is a typical machine learning flow. You can see where they sit in the machine learning lifecycle. With this, I'd like to hand over to Matthias for the H2O for GPU section.
Cool. Okay, so before I start, I have two questions. First of all, are we familiar with basic machine learning? So GLMs, gradient boosted machines, k-means, stuff like that? More or less? A few hands? Okay. Do you guys know what H2O.ai is? Like what we did? Okay, only a few people. So, okay, let me give you a very brief introduction. At its core, H2O.ai made an open source platform called H2O. We were a highly distributed machine learning platform. You were able to run us either on a single laptop or thousands of nodes. And we exposed to the end user those very basic algorithms. For example, if you wanted to predict a single number using regression, you would be able to use our GLM or boosted trees. If you wanted to do some kind of clustering or classification, we had also different algorithms for that. And it was all fine, but the problem was we were only utilizing CPUs. And after some years, we realized that most of our customers don't really need whole clusters. Like there's not really that many companies that make models using terabytes or petabytes of data. But we also noticed that GPUs are kind of fast, and usually with stuff like with new stuff like DGX-1 by NVIDIA, there's already enough memory for most of our customers. So we started thinking and playing around with GPU implementation of our already implemented algorithms, right? So for now, we implemented GBMs, GLMs, and k-means on the GPUs, achieving up to 40, 50 times speed up. One thing you need to understand about that is it really depends on your data size. If your data size is really small, there's this overhead of sending the data from CPU to GPU, about which Ashish was just talking about, right, in the previous slide. Like we had to go from one framework through the CPU, the other, etc. And it's always really, really slow. So if your data size is really small, it's probably still better to do it with our previous framework on the CPU. So just to elaborate a little bit on why GPUs are good for machine learning, like for this basic machine learning or for deep learning, because it's under the hood almost the same thing. As Ashish mentioned, GPUs, they have way more cores than CPUs. They are a little bit differently built. So there's this notion of latency and throughput, whereas latency is the time to make a task, to finish a task. Whereas throughput is the amount of tasks you can do in a period of time. So CPUs are highly optimized for latency, meaning if you have 6 or 20 cores on your CPU, you won't be able to do that many tasks simultaneously, only like a few or a dozen or 20. But usually if they are like very computationally expensive, they will most probably be finished faster than on the GPU. But if you have a task, if you have a problem that has many small tasks, which is the case in machine learning, GPUs will be better because, well, all of them can run in parallel. So, as I said, like machine learning under the hood is just like matrix optimization operations. So, for example, this is a very, very simple example of matrix multiplication, right? You take a row from the first matrix, a column from the second matrix, and you do pairwise multiplication and sum it, and you get your output matrix, right? So here you can see that if the matrices A and B will be really, really big, right? You will have a lot of those really, really small operations, those multiplications, right? So that's why, but the multiplication is usually pretty fast, right? It won't take you like days or whatever. So that's why it's really good to run it on a GPU. Like, for example, you can do row per row on a single thread and parallelize it. So as Ashish mentioned, like I read on like Buzzword, and I'm not really into talking. Like I'm a core engineer, so it's you can notice like the difference in slide quality now. So sorry for that. But I do have some graphs. So for example, a GLM is this method which can do regression, meaning, for example, you want to predict the price, right? So we implemented our own GLM based on a white paper from Stanford from Professor Boyd. And this is more, here we were learning 4,000 models. The data set was completely the same. We were using, if I remember correctly, US Census data. And on a double Xeon CPU processor, it took us like 6 or 7 times longer than even on a single GPU. This speed up isn't always like that great. With GPMs, sure, we also got it. And as you can see, like the more GPUs we get, like the time drops linearly, but that's not always the case. Like for example, k-means, which is a clustering algorithm. For example, you have a bunch of points and you want to assign them to different groups, like for example, to 5 groups or to 10 groups. We are still much faster than CPU implementations. So for example, TensorFlow, we didn't measure it against TensorFlow's GPU implementation for a very simple reason. There's no implementation. Because we are under the hood, our architecture is completely different. They are using the TensorFlow, which is really, really hard for those kind of computations. As you can see here, the problem with the brute force implementation is that whereas if you're going from 1 GPU to 2 GPUs, you do get, well, almost double the speed up. But then as more GPUs you add, the speed up is like not as impressive. We still think it's kind of a useful feature because GPUs inherently don't have as much RAM memory as your like normal RAM, right? Like it's normal to have even a terabyte of RAM in your computer, right? GPUs, the best ones now have, if I remember it correctly, like 16 gigabytes. But there's you can always connect them, right? So for example, the new NVIDIA box, DGX1, has 8 of them. So if you do 8 times 16, then that's 128. So we still think that's a useful feature if you have like too much data for one GPU. And I'm gonna.
Yeah, we have a demo coming up. Before we show the demo, just try to set this up, and it's only appropriate because I'm not a data scientist. So I'll tell you what is interactive machine learning. And the best way to understand what interactive machine learning does is to understand what the data science lifecycle or workflow is, right? And as you go from left to right, you do what's typically done. You collate and coalesce data preparation. You integrate data, you clean data, you enrich data. Now you got the data you need. And that's the time where you do data discovery, which is you find things, you find out what you're trying to do, what's your objective function. You find out what are the features which may be important for your model. So you're building out your model for that. And then you create a model, you score your model, you train your model, you validate the model. And then you use that model in your operational system. It's a CRM, SCM, ERP, to score against new data which you've not seen before. Use that model to predict values. And then, which is very usual, is that the model changes, the schema changes, the features changes, the business model changes. So you need to monitor, refine that predictive model, and that's a very iterative process. In fact, the first part is highly iterative. You go back and forth. You find out how well is the model working with data. And as you can understand, the data prep is the longest, the more clumsiest. It's called data janitorial work because you are actually doing a lot of, it's very clumsy. But it's not what I call a high order bit, in the sense that if you've really done fabulous with data preparation, it will not affect your business as much or your predictive model as much. The key thing lies in your feature engineering. Okay, feature engineering is what are the features we will use for your model, and these features are, are kinds where that's what a data scientist consider a unicorn, because he or she has to understand data, business, and data science algorithms at the same time. If they only understand data, then you can use some system to automate the data-driven engineering features set by just applying some correlation or covariance kind of factors on it. But the lift or C you can get on it will not be very high. What you really need to know is this feature from a business perspective affecting my model? For instance, we'll be showing a delinquency on loan data, mortgage data from Fannie Mae, a public data set. That's a demo about. And someone who's a business analyst who understands the business, let's assume I'm the person, I'm not a data scientist. This is where MapD really excels in, because it helps you unlock data. It helps you find out what are the different facets of data, what are the features may be important. You got to be careful, right? You want business-driven features, else you'll have garbage in, garbage out. At the same time, you don't want features that are highly correlated or just noisy, because it may lead to overfitting where the model is not going to perform well in real life scenarios. And Matthias can talk more about it, but this is more of a art than a science. And this is what MapD, and this is the area where you see the interactive machine learning part, where you will decide the features, add it to your model, run the model, come back, oh, that didn't make sense. That's the RMSE score is too high. And then the model validation is, Matthew should talk about it as well. And as you go after the predictive monitoring, now you have companies having sometimes thousands of models. In fact, the models, like I said, may go out of date, and you want to monitor it. The best way to monitor is in a very visual way, like what's the predicted versus actuals on the scatter plot? Is there deviation on it? Is there a new variable come in motion? So this is where MapD can come as well. It helps you visualize things to see how the model is performing. So without much ado, let's actually push forward to this. And I want to thank Vamsi if he's here in the audience. If we run into problems, he's the guy who created this, so don't blame me. And Vamsi is an intern. He started here a few months back. And this was just an idea in Bill's head. And this is a result of this co-creation between H2O AI group and Vamsi and a lot of people out here on our front-end team as well. But here's a typical example. Like I said, 1.1 billion rows of data from Fannie Mae. It's a public data set about mortgage data. And you can see, you can quickly look at different aspects of the data. loan group by delinquency, average delinquency rates, who is the servicing company. In fact, it's color-coded. If it's red, there have been more delinquent loans from this company. Obviously, this is one place you can dig into. Things which obviously you can have some hypothesis about is the current interest rate versus loan age. You can see, you know, your hypothesis is the interest rate is high, and as loan age increases, the bubble is bigger. And actually valid as well. You can see the bubble goes up. There's some kind of trend or variation if your objective function is delinquency. So as you look at these aspects, these are the features. You can assume current interest rate and loan age are a feature because even visually you can see for that objective function, there's kind of a trend line. It's not flat like this, which is non-interest bearing unpaid balance. I don't really understand that. But one thing I can, without understanding business, is I just look at trend line and you see it's fairly noisy out here, right? It's not showing you much. While someone who's a business user analyst will tell you, oh, it's not doing much because that's not affecting delinquency for these reasons. But like I said, certain things, if I was a business user, I would be able to zero in on. Also, I can explore information, right? So here, not surprisingly, you know, if a loan is modified, the higher chance it is becoming delinquent. You can brush across, you know, the loan delinquency days and the number of loans. So like I said, you're visually discovering data, your feature set, all interactively, and you've decided what your features are. So the next step is we'll take a data set like this thing, which is red in color, the Fannie Mae one, and Vamsi, it's not working. Sorry, I probably need to refresh it. So, okay, there we go. Last time, and then.
This doesn't work. Can we see the football then?
Yeah, that was my plan B. All right. So, listen. Like I said, this is the second step. You have collated your data. You've got a hypothesis. This is my objective function, delinquency rate, and these are the features I think I care about. The next step, I'm going to pass it on Matthias, is how would you do your model scoring and training? And I can type it in if you want to talk about what's happening.
Yeah, that would be cool.
Yeah.
So yeah, as Ashish mentioned, we will be working on that data set, and we have the algorithm is linear regression, so the GLM I was talking about. It's a regression type algorithm, so we will be trying to predict a number. The parameters you are looking at when you're doing machine learning, you have two types of parameters in your equation. You have parameters that we will try to optimize using an algorithm, for example, gradient descent, or in our case, the paper that I was talking about is called POGS, Proximal Optimization Graph Solver, I think, with a really weird name, which is a generic convex function optimizer. And as I said, we will be able to, with that, find the optimal parameters, but there's also this thing called the hyperparameters, which is a set of parameters that you as a user have to set yourself, like the algorithm won't find them for you. So in this case, that's alpha and lambda. What we can do with our implementation is like you can just type in how many alphas and how many lambdas you want to try, and we will try to, in a smart way, find them and like try them out and get to the best ones. N-folds is usually when you're training a data science model, you don't really want to use like your whole data set for training because usually you are overfit with that. So what you do is usually you split your data set into training and testing sets. So in this case, N-folds 4 means that we will split, this might be a little bit counterintuitive, into five chunks, whereas we will use the first 4 for training and the remaining 20% for validation. We will actually check how good our predictions during that model is. Is it done? No?
Yeah, sorry, I forgot to click. So
Oh, okay.
you need to keep talking for another 5 seconds.
5 seconds, yeah. Well, so in this case, we will be doing 8 times 100 lambdas. So that's 800 models on the GPU, each with those 4 folds.
Can we also talk a little bit about some other model or algorithms that you can apply to this kind of data, which is a continuous variable, right? Like
right. So another option would be to use GBM's gradient boosted machines, which is I don't know if you guys know Kaggle, which is this very famous data science competition platform, and XGBoost is apparently the #1 used. Was it the question?
Yeah, can you apply, the Microsoft one, the Light GPU is faster?
So we are doing benchmarks now. We are trying to benchmark it. Okay, so we're done. So yeah, so what you see here is the training RMSE, which is the root mean square error, the cross validation error, and if you want to do predictions, you basically just save it and then click predict, and you will be able to get your values. Does it make sense? Like with RMSE, it's basically we have labeled data, right? So we have our data points and we have a value. So using that, we can actually do a prediction and check it against that value, the original value, right? So if the difference is 0, that means we are doing a perfect prediction, right? So if we will do perfect predictions for everything, the RMSE would be 0. Like the higher RMSE, the worse the model is. And basically on that, that's one of the metrics that we are using here to actually figure out which model is the best.
Mm-hmm. Yeah, this is high RMSE value. I did not choose the right features, but in essence, as you can see from the steps of the data science workflow, now we've actually created a model and we'll deploy it in production. It's a very IT production work, and then you monitor and refine the model as time goes by to make sure the model is working perfectly. As the data changes, as the business model changes, the data could remain the same. I'm not going to run the predict, but just because it will take a bit of time to, we had some problems out here. And I'm going to switch back to a little bit about, what are the typical use cases? How would you apply this? Not just interactive machine learning, but the whole data discovery section. How do we apply it to AI? What are the common use cases you're seeing? So we'll spend a couple of minutes just talking about use cases. And one thing which I mentioned about MapD, the interactive visual analytics, is that what we do very well is in the intersection of where the data is large and your interactivity is both useful and business critical, right? So in the sense that if it is things, let's take an example, right? Things like fraud detection, for instance, response times are very important, and they're also business critical, as in you can save money by being highly responsive. And the big thing we do is we empower the analyst or the business user so that he can, like we just saw with the taxis demo, can come up with information and make them smarter. So it's basically a human in the middle kind of system as compared to the machine in the middle section where you completely automated the decision making to someone else. And as you can see, the typical industries where time is money, financial services like hedge funds, currency, trading, versus volatility and fluctuations. Fraud we talked about. In federal, a big goal is to keep things safe. So cybersecurity, situation awareness. Where the presence of food trucks around DC going around, are they dangerous or not? These are all threats they try to mitigate. Telematics, where your assets are your money-making units. So fleet management, incentive-based insurance. Telecommunications is fairly large, and we have a large number of use cases on that, or growing number of use cases on it. The large number of the data coming in through the cell phone towers and otherwise, rooms for optimization, for competitive positioning, to understand customer churn, to give them the next best offer. And like any asset industry like energy, oil and gas, utilities, all these have a very key need for information dynamically, demand response, smart meter analytics. All these are key areas where MapD is being used, or we foresee MapD being used. Finally, ad tech, and I'll give you an example to actually give you a sense of it. So Verizon Wireless, one of our customers, uses MapD. Well, one of the things they do is what's called over-the-air campaigns, where they try to understand, they send out pulses to understand what phones there are and get the events from the phone to do some analysis on it, whether it's offers or certain other things. They generate almost 100 million records a day, a large amount of data. And they were using, I guess I can say it, it's there publicly, they were using Impala, and it was pretty slow. It used to take them a couple of hours to analyze information, whether they're looking for iPhone 5s and where the location is and other information for running the campaigns against it. And it used to take them, like I said, a couple of hours. You can drink coffee, take a shower, come back, you're still running analysis, right? With MapD, you saw the instant responsiveness speed with large amounts of data, and they were able to use that to get, find patterns among events which are sent back to their cell phone towers from these OTA campaigns. In a sense, that's one of the things you'll commonly see is that patterns in data in real time. The other one is Simulmedia. It's an ad tech company focusing on audience segmentation for TV audiences. So TV audience, the Nielsen's of the world have collated large amounts of data. You have demographic information on one side, and network information on the other side is network duration, show times, all the things which are to do with shows are all lined up. And typically they help to advise these companies, Nikes of the world, how can they do their media programming and media buys against this information. Very complex. You can see a multi-factor analysis out here. And mostly what they want to do is they want to check, oh, this is my hypothesis. I want to go after young 18 to 24-year-old millennials, they're called. Should I go after the time slot of Game of Thrones or something else? I don't watch TV, so one of those programs. But in that sense, they want to do it interactively. They want to talk to their customers, who are the Nikes, and decide collaboratively how should they do their media buying. And in the past, what they did it was not a long time, it turned in 10 or 20 seconds. But it's like watching a movie, right? It's buffering. You're thinking, and you're not able to interact with it in real time. And they found us to be much simpler, using a smaller number of nodes and much faster to help them bridge the gap. So as you can see, a lot of these things are happening where you want to continue a train of thought at the speed at which you're thinking, and that's where we really help out as well. We have a growing number of customers. Like I said, you will see Verizon, who is from telecommunications. EOG is an oil and gas company. Fannie Mae in financial services. Jam City, which is a gaming company with millions of users, trying to use us for user acquisition. So lots of it. I won't go through that. I'll give Matthews time to talk about his section as well. Over to you, Matthews.
Right. So one thing that you can actually notice in my slides is like we have quite a bit of overlapping use cases, I think.
Yeah.
With MapD, that's why the collaboration is going so well, I think. So if you hear about the machine learning recently, it's mainly deep learning, right? And don't get me wrong, like deep learning is really, really cool if it's good for your use case. Like if you have this thing called what we call natural data. So for example, images, audio, text, etc. Deep learning is awesome, and you probably should be doing it. But if you have numerical data, and you can notice that like most of our customers, like for example, banks, insurance companies, healthcare companies, like they will have a lot of numerical data, right? They probably want to do some fraud analysis, etc. Then it's a good idea to actually start like with those simpler models like GLM, GBM, etc. Because well, it's easier to use, it's faster to train, and in most cases it actually gives you better results. So yeah, as I was mentioning, like just like MapD, a lot of our customers are using us for fraud detection. We've been in production at PayPal for I think months or years now, and from what they told us, like they are actually saving millions of dollars every quarter because of our model. There's a whole department, well, not whole department, we have one department who's like working with the cybersecurity and is trying to figure out ways to actually use machine learning to improve security within networks. We are also trying to get into healthcare more and more because, well, there's a whole plethora of use cases. You can do product recommendation, where by product I just mean like drugs or etc. Right? What's the best way to treat a given patient? Medical imaging and diagnostic, well, that's maybe more TensorFlow than us, true. But for example, there's this one huge use case that, well, unfortunately it wasn't us, but for example in Japan, where I'm currently based, Watson was able to actually predict a type of leukemia that like no single doctor in the world was able to diagnose. And the girl is actually living now. She was diagnosed to die within like a few weeks. And then they actually collaborated with IBM. They put in all her medical records, and she was able to actually, and Watson was actually able to actually figure out that it's like some kind of obscure kind of leukemia. So there's a lot of stuff going on. Yeah, we do have quite a few customers. Like we've been in the market for 5 years now. Our biggest ones being, I think, Capital One still, but we're trying to also get into retail more and more, eBay, Booking.com, and a few that unfortunately I cannot talk about. But if you want to hear more about use cases, you can actually go to our YouTube channel, and we have talks by people from those companies, because like I'm from H2O, so obviously I'm biased, right? But you can go there and actually listen to how they are using, like how their whole infrastructure looks and what they are exactly doing. And I think that's all.
Yeah, that's it. I mean, if you have any questions, either you can ask it right now or come up to us and talk to us. The map team is behind, so feel free to talk to. All right, then. Oh, you have a question. Go ahead, please.
So one of the problems we have in these systems is somebody has to schedule resources when there's intention for them. I mean, I can split my job between CPU and GPUs. I'm generally not using the machine alone.
Yeah.
Mm-hmm.
So as far as I know, neither one of you actually does that. So what platform do you recommend?
Yeah, I think that's a good. Maybe someone can answer that question more. Yeah, I think you're talking about resource management, right? So workload management, resource management, to ensure that there is isolation, no noisy neighbor problem, right? So that's your question?
That's a very I mean, there's a PCIe bus, which is one of the critical resources.
Oh, so
and then there's the GPUs.
Mm.
Yeah.
I can't get the data in there. I mean, it's a multi-dimensional scaling problem where GPUs is a relatively recent thing from Mesosphere, and they don't account to tell transfer times to get the data into GPUs in the first place.
Have you, what I know is that Kubernetes has GPU container support coming. So
yeah, there's that too.
Just to clarify, so if you're running data in that, you actually handle all that caching for you, optimize transfers, and put the data on the right GPU on the GPU system. Basically handle the caching transparently when the user doesn't actually look at it. I mean, obviously there's a broader issue of orchestration of multiple processes on the GPUs, which you may be using something like Kubernetes for, but NAFD is not purely GPU memory. We actually persist the data on disk, cache it in CPU RAM and then GPU RAM. It's almost like an L1, L2, cache thing. So all that's handled transparently.
In this context,
in this context, you're asking about training.
Yeah, and I've worked with the Kubernetes folks very closely, and nobody is doing scheduling of PCI bus. Which is a major bottleneck for both of you.
Yep.
Yeah, no, I don't disagree with that. I think we're still catching up with the actual production use cases. A lot of these are still alpha. What we saw the interactive ML is still alpha. We do need to get to.
I know you're not there yet. I'm asking which who are you working with, or are you just waiting for them to solve it? The orchestrators.
We're talking to some, especially AWS, Kubernetes, to find out more, but like you said, it's still exploring from still early days for us. We haven't gone into it as in beyond the alpha product. So first we're trying to solve the alpha problems, and then we'll go a little bit more to resource workload and isolation models. So
for the most part, right now, you'd say this is the private machine model.
At least for us.
yeah, at least for us. Yeah. But it's a good question. I think that's the next frontier when you actually have to make sure that you need to orchestrate things and create isolations and make sure it's all production ready.
What are some of the top things that most customers are asking for? Like you see kind of like the general patterns.
For the interactive ML machine learning part of things, if you're looking at use cases or scenarios or
The features they're asking for, like, or does your product right now meet most of it solves their problem? It provides value.
okay, yeah, and I should qualify this completely. This is very much still an art of the possible. We wanted to show a scenario like you see. There are three things happening. One is the GPU ecosystem, which was very isolated in silos. Even though HOAI and API run on GPUs, it had to go through the PCIe bus. So we solved that first problem by the GDF framework. The second problem was, now we've solved the data replication problem, was how do we get to the workforce, or its workflow, which is start with data discovery, feature engineering, model creation, and training. That also was done. But it's now sparked, to get to your question in one sense, with the early interactions with a really big financial services client and in a couple of other companies, it really sparked the inspiration of them, and that's what we're looking for. We're looking at customers co-innovate with us, and they're looking at it. Look, this is a common problem because either we do complete automation of our systems, which machine learning, where the models are not explainable, which is the direction we're obviously going in. This helps to unlock our business users so they can become the citizen data scientists. They can do it faster with the amount of data they use and do it much smarter as well. So it really sparked, and maybe Tor or someone else can reflect on it, because I think that was the goal. Is this is a project which is a very early art of possible. We're talking to customers to see what resonates with them and how it resonates with them. Todd, do you want to reflect some more on that, or?
I think so.
Okay, cool.
I mean, so just to clarify, relatively widely deployed in more classical kind of fast SQL or digital analytics use cases. This is a recent push in a partnership between us and Anacon and H2O, kind of embed machine learning or do end-to-end GPU analytics on our platform through this GPU data frame, which we're doing today. But the kind of more standard use cases for us are fast operational analytics, whether it's telcos, autonomous vehicle data, ad tech data, game data. It's pretty old hat for us.
So what do you like your customers like the whole lot? Do they kind of follow just the norm? Like what are they trying to connect this to mostly? What are the top?
Yeah, I think like if you look at our customers, say the majority of them use some kind of visual analytics. So a lot of that's Immerse, which you saw demo today. The nice thing about Immerse is that you can take tens of billions of records and slice and dice it interactively, not only using the speed of our backend, but also the power of the GPU to actually render data. You can also put a BI platform like Tableau on top. You see people build custom apps around it. And then there's the more kind of possible, just pure OLAP workloads. So hedge funds who need lazy trading, people replacing Redshift.
Well, that's kind of I was asking about the other end. Like what? So you answered what they're using to visualize, but what are they where are they climbing from? They're replacing Redshift clusters, or?
Yeah, so in time where you need fast we never claim to be like a big data warehouse replacement. So if you need every bit of SQL 99 or something, people often have the Teradata, or they have the Oracle Exadata, or whatever they have, right? But if you need very, very fast SQL, we've gotten increasing traction as our databases mature. We actually have one customer here replacing a huge cluster of Redshift with a single node of MapD. It's 100x faster, right? And we can do pretty complex SQL rate joins and such
You guys are using the Arrow or no?
Oh, that's not wrong. We have our own SQL, just because we have our own SQL engine underneath. We have a full compiler that can
Okay,
run
so you
SQL.
are.
Yeah, underneath the other domain that wasn't clear is there's a database. And that's actually our
That was what I was curious about.
Yeah, so
That's MapD core.
Matthew
Saw the
Core is
the LLVM.
and it's open source, so feel free to check it out. You can download the community version today. And that SQL frontier is kind of expanding for us, right? So right now it's basic, SQL 92, but it will expand and eventually cover Windows functions.
Yeah, I'm like Todd Mosback, the CEO founder of MapD. So, like you mentioned, what we don't think of MapD core, which is a SQL engine as a data warehouse. Data warehouse does a lot more data integration, data lifecycle management, data governance. But we are also seeing a lot of them using it to accelerate some of the workloads of Redshift. Or if they have used Redshift, which is overpowered for certain of their use cases, they're migrating to us because they need fast analytical processing. And that's what they care about. They will not use MapD for data integration, not for highly normalized tables. It's mostly analytical processing. That's a very common use case we're seeing as well.
Have you completed SQL 92, or is it 100% of that?
It's not 100%. We are mostly pretty close to it.
There's still some
There's some things in GPUs which are tough to do, difficult to do, but we are.
There's some things you'd actually never want to use. Like you'd be doing something a favor if you didn't.
Probably so.
Yeah.
Our big push right now is to basically get the PPCH compatibility. We're pretty finding a bunch of joint functionality that mostly get us there, except for its upgrades, which are otherwise engines. So it's not, our goal is not 100% compatibility. It's doing the main push of people's workloads. Like you said, not everything is useful.
Yeah.
So a place where you're documenting the gap between the spec and what you do.
Yeah, I mean, if you go into the documentation, it's pretty clear. I don't know if we say what we don't do, but we say what we do.
Yeah, no, it's right. So if you go to a
It's an exercise for the reader, like, oh, look, I've written 19% of it.
Yeah, you go to our community forum, you definitely see people saying, you don't do this and that, and it's a work in progress. But
Yeah.
The core stuff, the stuff queries, the joins, the stuff people use every day.
Yeah.
Can you expand on use cases for security?
Mm-hmm. So security, when think of cybersecurity or something else. When there's a demo which we can actually use to show. This is of.
Oh, it's not public.
Oh, okay. That's right. Sorry, it's our internal data, but it's a good time to get Todd up
I
here.
know
So.
it's up there. Put me on the spot.
Sorry, I'm putting you on the spot, but it will answer your question.
Is Andrew here? Is it MIT?
Follow up on
Yeah.
what in our Equitech?
Well, you can see to understand, because one of the shortcomings of a rule-based or a machine learning system is that the problem unknown. You don't have historical data, then you cannot create a model. Right? This is what, if you don't have with this, you definitely have the human in the middle who can see these anomalous patterns.
Okay.
And I
You don't have Michael here.
System or a machine learning system, which is a black swan event, right? In that sense, you've never seen it before. So, so from that perspective, the machine or predictive model is never going to
I don't know if we have it up right now.
Oh, sorry, I put you on the spot. Okay.
It's really cool. Trust me. Everybody loves it. We've actually had we gave this demo to a major kind of consulting firm, very active in the cybersecurity space, and they're impressed enough, even on our own firewall data, which is not that big, right? But being able to slice and dice that interactively, and imagine scaling that to tens of billions of records, looking for threats, looking for anomalies, that they're looking to build one of their major cybersecurity products around it. So definitely a major use case for us.
So mostly looking for patterns.
Yeah, you're looking for patterns, and I think the next steps for us are actually doing some automated insight generation where we can detect those. We can supercharge the analysts, right? So that it's not only the things that they find interactively, but we can actually tell them where the correlations or anomalies are.
It's also the precision of the mapping.
thing on the map, there's multi-billion data points. To be able to drill down to the most granular level. That's very exciting. So a lot of the analytics that you see won't go to that grain level. You see what they axes, measure that in cyber. Very cool. Yeah, because right now, my bank uses
We use Splunk.
Oh, okay.
So that's
Yeah, so actually, it's a good use case. So NVIDIA is actually working on an integration between us and Splunk where we can service the backend for analytics in Splunk. So if you're familiar with it, you could use it, but also you could use Immerse. This is not a cyber demo. I just wanted to show you a bigger example of scale. So Ash showed you 1.2 billion records. This is 11 billion records across 4 nodes. So you can kind of see we're zooming in here to the Bay Area, and again, you get the same basic interactivity, right? Where, you know, as I brush here, we can actually look at the oil tankers that sit there in the bay and get very granular and look at the, you know, we can even look at the grain level detail. So I could zoom down here from 11 billion to 1,895 rows.
Yeah, it's wind direction.
Yeah.
the turn on the anchor and the transponder in the same spot. So changes the long map, just the turning on the anchor. Creates these circles.
Yeah, and I think that's the demonstrate. Like you bring it to the cyber use case, right? Your IP addresses, your geo map, your IP addresses, and your temporal patterns, and you are able to slice and dice. So we don't downsample, right? All these 11 billion or more. You can actually see the bird's eye view and drill down with the single point with the IP address coming to you at a certain port, right? So those are things which of course, with the advent of additional automated insights, which you can do with GPU, help analysts and cyber attack analysts of the Noxa to actually catch some of these patterns. And it will always exist with some kind of rule-based machine learning system sitting side by side, because certain things, the machine, you can automate it and have machine learning predict cyber attacks, but the human in the middle will really amplify that and close the gap.
One pattern we reached about how much data is going out.
How much data is going out? There you are. See,
We don't care if the bad guy's in, but
Yeah.
if you cannot get the data out, we don't care.
that's a good point. The kind of data going out and how much data. That's a metric you can track in your record through your firewall and your network firewall. That's the thing you can look at. Like I said, that's a known unknown, right? So if you can create a rule-based system, saying how much is going out. There are certain angles of attack and vectors of attack you've never seen before.
Yeah, we're using it now, but it's slow.
It's slow.
Yeah, it
Yeah.
doesn't scale.
And
Absolutely. That's a recurring problem we've seen. It's something that we're,
But it's a bank.
one of our earliest customers, 30 billion records. They could not scale that in Splunk, or even if they wanted to, it would cost them like tens of millions of dollars to get to that scale. These are military ops boats. If you want to see what the government's doing here, they tend to sit here. I don't know why. Is it skinny? Let me just see if I can. Right. Okay, here it is.
All right. I think you can see.
Okay. All right, so here is our own firewall data. So it's like sharing your own dirty laundry. This is a relatively small data set for MapD. It's 137 million rows. But here you can see all the points on a map. You can see the basically the top IP addresses, the out-in. So immediately, if I was kind of a network administrator, I might want to look at what's coming in that's blocked. No man's land. You could see this showdown.io. That's actually like an internet port census. So if I clicked on it, I could see that they're basically pinging our ports in relatively equal proportion, just looking for any ports that we have open. So here you can see immediately like there's this huge spike. And if I drill down on this around August 15th, right, we can see immediately where it's coming from. It's coming from China. They're hitting port 25, 471. We could drill down farther and zoom in. Oops. And even get down to the individual servers. So you can quickly do this ad hoc analysis to kind of see where threats are coming from. I'm sure somebody who's more of a domain expert could find a lot more interesting stuff in the data.
How do you see inside their network?
Oh, you need the special NSA spy pack. That's sold separately. Battery's not included.
Trust me, it's available everywhere.
It's available everywhere, yeah, exactly. So,
Yeah,
Gives
this
you
is
an
what
idea.
I want to talk about.
Just curious, did you base this on Metron, Apache, or are you doing your own?
Andrew? Oh. I'm left here alone. So this is coming off our firewall data, and somehow we just pushed it globbed it into a tabular form and pushed it in. I'm not an
Metron is
expert.
the Apache project you use for sort of the security stuff.
Oh, okay.
Okay.
We should check it out. Yeah, I was not familiar. Very cool.
Yeah, it's not the visualization stuff. It's actually intended to be this.
Okay. Interesting.
Not sure I really like it. I was just curious if you use it.
No, yeah, I think we just probably did some, SAD and knock to get it in the right form, but I'm sure there are better tools out there for it. Just more a demo, right?
I'm not sure it's better. It's just probably worth knowing before you reinvent the wheel.
Yeah, well, I think the point here is just the scale, right? So, none of this is pre-aggregated or indexed. I mean, imagine it's 137, but this could be 100 billion records. And, slice and dice it, eventually do machine learning against it real time. But I'm sure they have a lot of specialized functionality.
If you can accelerate the existing platform, these that one's open source.
Cool, yeah,
Yeah, good
definitely
point.
check it out.
Thanks for that. Yeah. Great. Thank you. Thank you all for coming.